Hello, everyone. My name is Leo Fan. Today, I'll be hosting another OpenFOAM and combustion simulation webinar. So today, the topic of this seminar is modeling of turbulent combustion using OpenFOAM platform. And our guest speaker today is Professor Bai. So I'm delighted to introduce our speaker. So Professor Bai joined the Department of Energy Science of Lund University in April 1995. Where he had a research group in the division of fluid mechanics, focusing on reactive fluid dynamics. Professor Bai received his PhD degree in fluid mechanics from Royal Institute of Technology, Sweden, in 1994, and he's docent from Lund University in 1997. He became senior lecturer in the Department of Energy Science of Lund University in 1999, and since 2002, he is a professor in the Division of Fluid Mechanics, Department of Energy Science of Lund University. Professor Bai's research interests include theory of flame propagation and extinction, mechanisms of pollutant formation in chemically reactive flows, modeling of turbulence chemistry interaction, direct numerical simulation and large eddy simulations of turbulent reactive flows, modeling of solid gas and liquid gas turbulent two-phase reactive flows, with application to different energy conversion process in internal combustion engines, gas turbines, and biomass furnaces. In 2018, Professor Bai was elected the Fellow of Combustion Institute. And the floor is yours, Professor Bai.
Thank you, Leo, for the kind introduction. Thank you, Huang Wei, for inviting me to give a lecture here in the wonderful seminar series. I start by telling by listing the contributors to this talk. We have many former and current student postdocs who has been using OpenFOAM. The first one I would like to mention is Magdi Jiangji, who is currently in University of Birmingham. And he and Dr. Richard Schürholt, they are the first students and postdocs work using OpenFOAM. And later we have many other students here, at least I'm not going to read all of them, who has contributed to this work, to the talk today. And I would like to thank the Polytechnic, the Milano group, Tommaso, Gianluca, and Federico for sharing their OpenFOAM codes and experiences in the early times of our use of OpenFOAM. And we collaborate with the Norwegian University of Science and Technology, Professor Tian Li and Professor Therese Lovas, who shared their two-phase particle fluid bed code, base code with us. And we also have to thank TU Edhu and Professor Somers and Philip Dubois and others for sharing their FGM model. We work a lot also with our neighbor, Technical University of Denmark and NAN, Professor Jens Walter, lead a group also using OpenFOAM. So by that, I would like to give a very brief introduction to the university, Lund University. For those who do not know the university, we are in the southern part of Sweden, here roughly, pretty close to Copenhagen actually, with Lund. If you look at that, this is called the so-called Øresunds region. Here is the Baltic Sea, and here is the Atlantic Ocean, Norwegian Sea. And we are here and very close to Copenhagen Airport, which is here with a bridge. So welcome in the future, if you guys, some of you are visiting the region, please contact us and we'll be glad to host you. So Lund University is one of the research center, combustion research in Sweden. We have many divisions, departments, physics department, engine division, fluid mechanics, which is what I'm working, thermal power engineering division, heat transfer, fire safety. We share common interest in combustion research. We are the Lund University Combustion Center, and we have had competence centers studying internal combustion engines. The ACCCI work and low temperature combustion work in KCFP has been very well known in the world. CCOST is a national center, Swedish National Center for Combustion Science and Technology. In Lund, we have roughly 10 professors and more than 70 to 100 researchers, including PhD students. Lund is well known for its laser lab, Anatolian lab, which has a dedicated building in the first, in the base floor and first floor. There are many labs with highly equipped laser facilities, including optical engines, and a high pressure rig for gas turbine studies. So our group, we are 100% numerical. We're doing safety simulations. So we perform fundamental research, studying turbulence and turbulent flame interaction, spray combustion. We also work a little bit with combustion chemistry, but we are not really expert in this. We're working on flame theories, flame structures, flame instabilities. These are the fundamental aspects of combustion. But mostly we carry out research with applied nature. We collaborate with Siemens industry gas turbine. We collaborate with Volvo, Scania, MAN, Wärtsilä. MAN is in Denmark, Wärtsilä is in Finland. We collaborate a lot on engine research. Currently, we are working with MAN, Wärtsilä on ammonia hydrogen marine engine. So this is one of the hot topics in the current research. So power industry, we work with the Danish company, or it's an international company called Babcock, and local company Crafting on waste combustion or biomass combustion. We have fire safety also of interest. Most of our research are funded by Swedish local, but also we have EU and industry projects. So here are the pictures of the devices we've been working. Siemens SCT engines of fixed bed combustion system, cars, and the aero engines. So regarding the use of OpenFOAM, we have been studying in the recent years, mostly focusing on low temperature combustion. That's because internal combustion engines. That's because we have a center, KCFP in Lund. There are many test beds, I think around 15 test beds in the engine lab, where we carry out numerical studies on ACCI engine, reactivity controlled compression ignition engine, partially premixed combustion engine, which is a compression ignition engine. We also work with the dual fuel marine engines. Currently, we have an EU project and the Nordic countries collaboration projects on ammonia hydrogen marine engine. And like other groups, we also use ECN data to validate our spray model and spray flame model. So we also, like I said, using safety simulation OpenFOAM based to simulate biomass combustion and gasification process, considering both grate fired and fluid bed fired system. we also currently have a ongoing work on metal combustion CFD modeling based on OpenFOAM. Our group also recently, or in the past few years, have been interested in high calibration number flames. There are many good experiments carried out in the combustion physics division, led by Professor Marcus Arding and Professor Zhongshan Li. We collaborate with a lot with the COST group, the robots and Amen on studying swirling non-premixed flames, partially free premixed flames. They did excellent experiments. We collaborate with them and trying to be able to simulate such flames using OpenFOAM. We also did some DNS work using OpenFOAM. One of the work I can mention is where we published a combustion flame in two-chamber internal combustion engine with a pre-chamber and main-chamber combustion system. In terms of model development and implementation in OpenFOAM, because we are interested in low temperature combustion, which is typically simulated using relatively detailed chemical kinetics. So one need to integrate chemistry to flow solver. This is very time consuming. It could take with OpenFOAM several weeks. So to simulate one engine cycle. And there is, of course, it depending on the chemical kinetics, how large it is. So one of the work we've been trying to do is to speed up the simulation by introducing something called the chemistry coding mapping approach, which I'm going to talk a bit today. This type of chemistry interaction integrated to the flow solver, there is the issue of flame turbulence interaction. One can use partially stirred reactor or PDF transport PDF. And transport PDF is very expensive. So CCM can be really helpful when we use PDF transport PDF model. In our group, we especially prefer to use Eulerian stochastic fields method with one of the methods. When we use this, our student, Dr. Lele Xu, who found that there is an issue of element mass conservation. And this is not much talked, but we met this problem. He found that when you use the method, there is the nitrogen species is getting lower and lower, and you get more and more fuel when you matching in time, and that's because of element mass conservation problem. So we try to find a way to get rid of it. I'm going to talk about how we do that. These are detailed coupling, direct coupling with chemistry, but FGM model, many of you know it. FGM model tabulation approach is really the preferred one if it's accurate to do such simulation. However, for low temperature combustion engine and many other applications, the FGM dimension is very large. It can be very large. So the FGM table can be many terabytes. So it's very difficult to be used in engine simulation. So our student Yan Zhang, who with others developed the AI-assisted tabulation approach, so to reduce the memory requirement. Another issue of FGM model is presumed PDF. One often uses presumed PDF to integrate the table into the flow, mean flame calculation. So since we have an ESF code, so we Hamed Harpo and Dr. Janzi and others, we developed the integrate ESF transport PDF for the FGM variables, so to replace presumed PDF. And this is going to be, I'm going to show how we did that and the results. So if I have time, I want to also talk about the solid gas two-phase combustion under dense particle condition. Unlike a spray, which we assume diesel spray, which we often assume particle, point particle, we don't consider volume. But in fluidized bed, it's a dense particle situation, so particle collision and has to be taken into account. So we get a code from NTNU, which is based on multiple phase particle in cell and PPSC approach. And we further extend it, make it more robust and accurate by introducing a distribution curve method, DKM. I'm going to briefly discuss this. Like I said, we have also DNS solver, which is basically OpenFOAM integrated with Cantella. So, but I know that last week there is an excellent DNS work being reported. So I'm not going to talk about this today, but we do have such a facility or code. So let's talk about the finite rate country coupling with the flow solver, which we call coordinate chemistry coordinate mapping. The basic idea is that in most combustion process, we have a large number of species and large number of reactions. So here it shows 2D DNS of a hydrogen air premixed flame. Due to differential diffusion, you can see the flame is actually highly wrinkled and with the cells that is due to diffusive thermal instability. Here, front part has a very high temperature, where in the trading, there is low reactivity. This is due to the differential diffusion. Originally, a perfectly premixed mixture, like here, benzone, perfect premixed. It could develop to element mass H atom or element H element is actually focusing and defocusing. And this is very well known. I'm not going to discuss the physics. What I want to say is that there are similarities. For example, this point and this point, many of these points, they are very similar in terms of both differential diffusion and combustion progress. So therefore, integration of each of these points can be done at once in physical space. I'm going to talk about this later. This is another example, HCI combustion, homogeneous in composition, but inhomogeneous in temperature, which gives inhomogeneous ignition. Some of these parts ignite first. This can also be considered as one very similar thermodynamic state. So grouping them or mapping them to physical space, phase space, and then integrated in phase space is the basic idea of CCM. So in talking about low dimensional manifold, we can say that there are a number of examples of low dimension manifold. For example, in non-premixed flamelet combustion, mixture fraction can be considered as one low dimension manifold coordinate. So if you express other species in mixture fraction coordinate, you will see very good correlation along the flame, along different parts, in different parts of the flame. So this is an example of low dimension manifold. For premix combustion, progress variable is one of the low dimension manifold. Homogeneous charge compression emission, HCCI, progress variable or temperature is an example of the dimension low dimension manifold. So one can see that the idea of flamelet combustion or flamelet model, to me, it is make use of the low dimension manifold concept. So flamelet tabulation approach for premix and non-premix flames, level set G equation approach for premix flames. These are all based on the assumption one can utilize one dimension flame coordinate to map the species into this coordinate. CCM use the idea of low dimension manifold, but it's not a tabulation approach. So what I mean here, we use the species transport equation as an example to express what we do with CCM. Here we have the time term, convection term, diffusion term, and reaction rate term. Using a fractional step method, the reaction rate term is integrated within a flow time step using very fine time steps, solving this problem. Because of the many reactions which has species with a short lag time, reaction rate, it's like a spike in time, spike function, a delta function. So one need to use really fine time steps to integrate chemistry. This integration step will generate something like intermediate state species and density with a star. And then based on these, one can do the convection and the flow simulation, convection, diffusion, integration. So depending on the order of accuracy in time, one can do different combination of the steps. But this is the basic idea of fractional step. So CCM, the integration, like I said before, is done in phase space. So here, for example, we have many points share very similar thermodynamics variable, very similar. So if we have the same species, Y, K, T, P, N, then the chemical reaction does not really know the flow. It just reacts. So one can integrate this reaction in phase space like this, and then get the vessel and go back. And then the convection diffusion or strand differential diffusion, they are all taken account here in these steps. So what is phase space? For example, here it shows two different phase space. Temperature is the vertical coordinate, and the horizontal coordinate is element, either element C or element H mass fraction. One can see element C is almost homogeneous. So therefore, it doesn't tell the difference between this point and that point, this point and that point. So obviously, elemental H mass fraction is a better choice for phase space. So because it tells the difference. So in this flame example, we use 3D dimension CCM. I'm going to talk about later. So we test the CCM method using DNS, okay? Because here we don't have a modeling issue. So CCM is an integration of chemistry just. So this gives us a cleaner case to compare. So we tested the 6 different cases under different temperature, equivalence ratio, hydrogen flame. We choose lean flame because we want to see differential diffusion effect, 3D, 2D, and also methane air flame or syngas air flame. I'm going to just show you one case, case 3, which is a lean hydrogen air premix flame. This is DNS without CCM. And this is a prediction using DNS with the CCM, CH and CT. From our naked eyes, we see that these are very similar. Of course, one can define a numerical error by checking the difference at each point and using the L2 norm and to define an error, which is actually rather low. So what about the speed up? CCM speed up, this is case, the 3-dimensional DNS case, which is a factor 5 speed up. So with the CCM, one can have 5 times faster. The other cases, 2D cases usually, and 3D cases are usually faster because there are more points share similarity. But anyway, it's 3 to 5 times speed up. So question is, how do we decide the CCM coordinate dimension? And how do we control error? So CCM is not an automatic mathematical approach. It's actually based on our physical understanding of the flame. So we need to understand the flame behavior or ignition behavior to decide the CCM. Once it's done for a similar problem, one can really use the method in a very efficient way. For example, perfectly premixed mixture with a stratified temperature, which is ACCI engine type of combustion, CCM can be just 1D. This is temperature. And one can, some of you who knows, familiar with the earlier works of ACCI, people use multi-zone method to compute really the ACCI engine. They group similar temperature points and do the integration just using 3 zones or 9 zones for the whole cylinder and get a very good pressure trace. So this is a typical CCM with a 1D. Perfectly premixed flame, but with a differential diffusion, like the case we studied. We found the 3D CCM is needed. Temperature, mass fraction, element H, and also gradient of element H. This is representing the strain effect or flame stretch effect. So with the non-premixed combustion or partially premixed combustion, in addition to this 3D, we usually typically need a mixture fraction. With a few that has a low temperature chemistry like N-heptane, we found that the low temperature chemistry part need another dimension, few mass fraction. So it can be a high dimension, but it's really that when you map to the physical phase space, even though it's high dimension, but not all this space is filled with the physical quantities. So therefore, actually, there are only a few number of particles, points in phase space. So error is controlled by phase space resolution. But in case you have a few physical space points which cannot be mapped really to the phase space, in case you choose a low dimension phase space, then you can treat it as a standalone physical space points. So it means that you do the integration of the phase space points individually. So this is absolutely accurate, but there is a penalty of computational time. So here I want to show you an example of using CCM, simulating ammonia unheptane combustion under ACCI condition. This one is based on the ECN spray H setup. These with hot air in the surrounding, and then injecting unheptane here, liquid unheptane points, particles. And this one we have in the ambient gas, we have 5 based on ammonia 0.2 mixture, pre-mixed mixture of ammonia and air. And here with a higher. So I'm not going to talk about the physics again, but I can show that what is going on. We have liquid droplets here, and then suddenly we have the cool flame or low temperature. And then we have a high temperature ignition indicated by OH. And here is the liftoff length. The onset of OH, the timing of onset of OH is the so-called ignition delay time, IDT. The liftoff length is, so LOL. There are, in the ECN case, the experiments, there are measurements showing the onset of the IDT and LOL. Important thing I want to point out with the ammonia, the onset of ignition is delayed further with the increasing equivalence ratio. So ammonia prevent, inhibit, or suppress the ignition process. Another point I want to make is the distribution of NO and N2O in such a flame. Actually, N2O is only on the thin layer surrounding the hot region, center region. So N2O is greenhouse gas species with high impact. And such a study indicates where N2O is formed, and perhaps one can find a way to get rid of N2O. Okay, coming back to CCM speed up rate. So for this case, unheptane spray H case, we have calculated the time, CPU time needed for total CPU time and the CPU time consumed in the chemistry integration. Initially, before ignition, the chemistry time, of course, is very low. But during the stationary flame stage, roughly 80% within using a mechanism of yaw, 54 species, 269 reactions, roughly 70–80% of the time is actually for the chemistry integration. Here shows 2 models: WSR, worsted reactor, and stochastic fields method. This justifies the use of CCM. This figure shows the ratio of phase space point to physical space point. So one can see that each phase space point corresponding to roughly 20 physical space points in this case, or 30, depending on the model we use. Of course, in the low temperature ignition stage and later burnout stage under injection, the cells in the phase space, one phase space can represent 100 or 70 or 50 points. So it doesn't mean that CCM will give you 20 times faster because of penalty of using. You need to do indexing, you need to do the mapping back and forward. That will take some time. So essentially, we found for spray combustion, spray D here shows 20 million cells, we can have 3 times faster. It means that a case usually takes 3 weeks. Now you can get it done in 2 to 3 or 1 week. So due to parallelization, if you use more cores, it's a slight slowdown, but this can be improved, I guess, with more effort. So by that, I want to move to PDF modeling work that we done in our group. So we use Valino's high-range number version of formulation of SPDE, stochastic partial differential equation. The basic idea of ESF is when you compute physical variable, either LES filtered or runs time averaged or ensemble averaged, you obtain this mean variable from ensemble of NSF number of stochastic fields. So each stochastic fields, the nth stochastic fields satisfy this equation, which contains convection term, diffusion term, macromixing term, Wiener term, which bring into stochastic property of the in the Valino's SPDE version. And also this is the reaction rate term. So the Wiener term here is include eddy diffusivity or SCS, total SCS diffusivity, and then a gradient of the fields, and times DWIN, which represents the increment of Wiener process. It's different for different n, but independent of spatial location. It's a homogeneous in space, but not isotropic. So one can allow a different number in different direction. So remember this equation. When we do summation over all phase, all stochastic fields, summation, and over all species, NS species, we see on the left-hand side, we obtain the sum of all species mass fraction. We know that this one should be 1. On the right-hand side, however, because of DWIN waiting for the gradient term, this is not 0. So this means that using this method without care, one will have a situation that the mass is not conserved. But in OpenFOAM, typically one do not solve all the NS species. Instead, one use 1 minus the rest to maintain sum of these species equal to 1. This is okay when this part is not deviating, or this part is not contributing to too much. So a typical solution method for the ESF is the so-called 3-step factorization scheme, which is solving the convection, diffusion, and Wiener term first to get the n fraction, the first fractional step. And then one compute the mean variable for the first step using this. And then the second step, when integrate the micromixing term, and in the final step or third step, one integrate the chemical reaction term. So finally, one can compute the new time step thermodynamic variable using this in some average. So we're applying such a model to simulate a simple turbulent count flow flame. One can see check the mass conservation problem along the center line, because along the center line there is an analytic solution of the mass of each element. So numerical solution minus the analytic solution will tell the arrow or the change of element mass of C, O, and H, and N. One can see that if you use the conventional stochastic fields with the 8 fields, you get such a 10% of arrow. Ideally, it should be 0. Should be totally mass conservation, element mass conservation. Although the increase in the number of stochastic fields can decrease such an error, but usually in OpenFOAM engine simulation, 8 fields is often used. That's because we use more fields, like 32 is much more expensive. So what we did, we have this work recently published in Combustion Flame. We have modified the factorization scheme. This was Dr. Xu and Dr. Shen-Hui-Zong, and they're very clever, and they wrote these codes in OpenFOAM. So step 1, we do the integration step of convection, diffusion, and Wiener term. It's like the conventional fraction step. And at the same time, we do an intermediate step. It's 1, but it's not entirely 1, but with a star. In this one, we do not have the Wiener term. So in fact, if you don't have the Wiener term, the stochastic fields in some average is equivalent to this equation. So anyway, we got the star state, mean variable. And then we can check in the arrow, summation of these minus that. So if the Wiener term, summation of Wiener term should theoretically become 0. So if it's not 0, then it's indicated in the arrow. So we uniformly distribute the arrow to the stochastic fields of the n. So this is acting like a correction. So we get the second step. And we can see now this in some average of this step will be exactly like the 5 star. And this, since it's a convection diffusion, it is automatically guaranteeing element mass conservation. So this is mass conserved. And the third step, we do the maximum mixing term. So after this step, one should do the chemical integration. However, we found another issue because of the Wiener term and because the fact that sigma psi these stochastic fields is not physically realizable. The sum of it is equivalent to the mean thermodynamic variable, but each of the fields may not be physical. It means that some of the species may have a negative mass fraction, for example, or mass fraction larger than 1. So in OpenFOAM, one usually use a limiter. If something less than 1 mass fraction, then one can make it equal to less than 0 and make it equal to 0. Larger than 1, make it equal to 1. So otherwise, in the source term or chemical reaction rate term calculation, you're not going to be, the code will not be happy to see something that is less than 1 mass fraction. So we apply a uniform limiter instead of an individual points limiter. So in this way, we can show that it behaves better, and also it is mass conservation. So now the same case with ESFC, we 8 stochastic fields, we get a identical 0 error. So this shows the improvement. An application of the model to simulate the cost swirling partially premix the flame with a local extinction and reignition phenomena. Zooming this part, one can see applying the original stochastic fields and the modified stochastic fields indeed give certain difference. Note here we have at 0 time everything starts from the same initial condition, and then after 1 microsecond, one see that there are some difference already showing up. Here shows an earlier extinction than these and then this original model scheme. Here shows an earlier reignition. So anyway, it makes some difference. So for the same case, one can see that the convergence of Wiener term, like I said, if you use a larger number of stochastic fields, for example, 64 stochastic fields, the sum of the Wiener term, in some average the Wiener term, is actually converging to 0. However, if you use 2, this is very big. 8 is not negligible. But if you use the modified model, then it's identically 0. Here it shows that the mass error accumulated in time in the domain that in the Zoom domain, one can see that element mass of C actually is increasing. Element H also increasing. O is not changing a lot. It's slightly decreasing, independent of number of stochastic fields. So this is what we see that for the engine simulation that we get more fuel in the system if you have such an error. But with the modified fields, modified ESM model, it's actually converging. It doesn't accumulate much of the. I have to speed up. So I move to the FGM work. In the FGM work, we we did the 2 improvements. But before showing the improvement, I'd like to give a very brief introduction of the FGM. So this is also like a low-dimensional manifolds. So a physical space can be mapped to physical space. So in this case, Cassie. So one can tabulate the species distribution on the low-dimension manifolds, FGM variables. So CAM1D or Flame Master can be used to generate such a table. FGM tables for engine simulation usually contains 4 variables: mixture fraction, reaction progress variable, pressure, and enthalpy of the oxidizer. So we utilize FGM simulate an engine, which is where we are lucky that we have a paper going to be presented in the symposium to come. It's a cost engine, which is an low temperature combustion engine. I think this is a PPC engine with PRF 70 fuel, means that 30% of N-heptane, 70% isooctane. With such a fuel, there is the fuel mixture liquid. When you inject it, they evaporated differently. So our contribution is that we propose to use a 5-dimensional FGM, adding a mixture fraction based on N-heptane on top of mixture fraction itself. So the simulation, largely the simulation tells the combustion, high temperature combustion, and the low temperature combustion and temperature, and also the mode of combustion using sigma, indicating by sigma at the different kernels. I don't have time to talk about this paper, this work, physical interpretation much, but I want to show you that the FGM model is actually can capture this pressure trace. What about what I want to say is that in this 5D FGM tabulation, we use the FGM table is actually 14G. It's very large, and this is not the largest. If you use more complicated flames, it can be even larger. So the tabulation, very large tabulation, is a problem of FGM. So this comes to the so-called difficulty of dimension. This is a very large data system integrated in the flow calculation. It's very time consuming. Dr. Yan Zhang, who was a visiting student from Tianjin University to our group, he developed the AI mapping, AI approach, trying to use AI functions using AN to represent the database. So here, FGM AN function, FGM data for species, this species, and for this species, and for the field, one can see that it can have a perfect matching for this species. And for the worst species, among all species, one can see that the correlation of the FGM and AN data can be rather good. So since we have AN, then we have AN function instead of FGM data. So the data need to be stored is much less. FGM and AN, you can see that they predict almost identical flame structure. In terms of IDT, the IDT, FGM original, FGM AN, they simply overlap. LOL, lift-off length, is also overlapping. So this is spray edge simulation. So it means that this AN approach is actually rather good. One can see that FGM without AN, usually for the spray case, we simulate 3 days, but one need 1 terabyte memory. With AN, it's 100 megabyte. So we get a much lower demand on memory. And of course, we can see that here comparison of FGM and the ESF, and these will take 30 days. So FGM is really a way that can have fast solution prediction. Another issue with FGM is the use of presumed PDF. This presumed PDF is not necessarily, people use it, but it is not always accurate. So what we did was to combine FGM with the ESF. So the common thing is that with the tabulation is the same. However, we are using a stochastic field solution to calculate the FGM variable. So in this case, I'm showing 3 FGM dimension. So using stochastic fields equation, solve the variable to replace this presumed PDF assumption with the mixture fraction beta function, progressive variable delta function. And here it shows the results of spray A, ECN spray A simulation. One can see that the calculation can capture the ignition process. Here shows the formaldehyde blue, a line of the formaldehyde blue, and this is formaldehyde, and then OH. And the experiment shows the chemiluminescence and pseudoluminosity. So the work is, some of this work is presented in a new paper, Combustion Flame, and also in the symposium. So we can see that ESF with the FGM can improve the prediction of IDT. And also here is a little bit strange, but it shows that with the correct numbers, stochastic fields, one can capture better the experiments. However, with the more stochastic fields, it's not giving a better prediction. This is a little bit mystery. We need to investigate it further. And here shows the pressure trace, pressure rise, with a presumed PDF and with ESF. One has to say that if you tune other spray parameters, maybe with the presumed PDF, you can also capture that, the experiments. I guess some of the group did that. We use without tuning much. We found that the ESF FGM can directly capture that, this flame. So if you look at the difference, FGM with the presumed PDF, it's actually PDF distribution is here. It's a narrow band in progress variable space, but with a special distribution, with the distribution mixture fraction space beta function. The real stochastic field simulation gives such a PDF distribution. So they are not independent. Here is assuming independency, progress variable, and mixture fraction. Here it shows that it's not, depending on where you look at the problem. So I'm already about to finish, but before that, I want to briefly tell the work we are doing with the fluidized bed simulation. In fluidized bed, there are many sun particles and fewer biomass fuel particles, and they interact in such a dense two-phase flow problem. And we, near Lund, we have a very modern, newly built biomass-fueled power plants with a 50 megawatt capacity. Here, using fluidized bed technique. And this company is our industry collaborator, and we promise to do simulation of this boiler. However, we face great challenge. Here is the sun particle and biomass particle, sun particle, and temperature of the particle and animation. What I mean is that the two-phase dense particle system, one typically use a DEM approach, or MPPIC. We use MPPIC because it's economical. And there are too many particles in the system. In the fluid bed particle power plants, we have 60 tons sand particles, which roughly we calculate it's 10 to the power 12 particles. You never can trace such a particle, such number of particles. So therefore, one trace parcels instead of individual particles. For example, we can choose 1 million parcels, and each parcel is actually contains 1 million particles. So if you happen to have a very small cell, CFD cell, then your volume of the particles will be larger than your volume of the cell could accommodate. This is the problem. And what happens is that the code will have very small, very large solid volume fraction, even larger than 1. And this means negative void fraction. So this means that in OpenFOAM, usually you use a limiter. If the void fraction is less than 0.38, then you set it to 0.38. You never allow it to be negative, then the solution will be collapsed. And this will introduce error. And actually, it is also giving a problem of convergence. So what we do, this is the original PCM. Equivalently, one grouping clustering the particles in a neighboring place into one cell. What we do is we do the reverse process. We numerically distribute it to the surrounding. And this type of work has been done also in the literature for single particles, for small systems, but we implement to OpenFOAM. And this work is just recently published, and we tested the problem using a very simple reactor, and shows the dense particles in the lower part of the bed. And this shows that with the original method and with the new method, this figure shows when you use coarse grid, okay, then you use less parcels. However, the coarse grid solution, we know that CFD doesn't like coarse grid very much, so you want to refine grids. So then you need more parcels. So coarse grid, medium grid, and fine grid. And this will give you the similar loads, means that a volume fraction of the gas in the distribution. If you use the coarse grid, but you use less parcels, then you have a divergence. So this the triangle means diverged solution. So this PCM means that if you use fine coarse too little parcels, then you will have divergence. So with the DKM, we see that it never diverges. So we can really work with even higher carrier load. So it means that we almost get an independent mass spacing and particle, this normal particle. So you don't need to use to correlate them together. The computational time is rather similar. And here are the comparison with the experiments with the PCM, DKM of the mole fraction of the gas fire product after the outlet of the gas fire. One can see that particularly with the different grids and number of parcels, the new method is less sensitive. More importantly, with this method, we actually can get a solution for the big boiler. Otherwise, we never get a solution for that industry boiler. So here, this link where we share some of the OpenFOAM codes, and more information about our research projects are found in our homepage. So I'd like to acknowledge, thank our sponsors, and I stop here and use a very long time. Okay, 1 hour, and I'm ready for questions if you have any. Thank you for your attention.
Thank you very much, Professor Bai, for the comprehensive introduction of your group's work. So we have a few questions from the attendees. So first one, we have Pin, who is from Jiangsu University. So his question is about CCM is a low-dimensional manifold, but not a chemistry table. So in what format do you provide the chemistry information to the flow solver? We know one has to prepare a table for the simulation, for example, FGM or a G equation. But for CCM, I'm not very clear how it provides the chemical information to the DNS. Yeah.
Okay. Thank you, Ping. Nice to see you. Ping Wang was my former PhD student and was a professor at Jiangsu University. Okay, CCM. We don't need actually any table. That's a good thing. It means that after each time step, we redo the mapping and we do the integration in phase space. So these will a little bit more time consuming because we do the regrouping mapping every time step. However, this is the best accurate approach. One can think about tabulate some of the previous time steps, perhaps like other approaches, like I don't know, ISAT or something idea. So here we don't do any saving of the previous time step information, just to get rid of this memory issue. So I don't know if I explained it. But for more information, Ping, I would like you to check the CCM paper in CTM.
Thank you very much. We have another question from Hao Chen from Shanghai Jiaotong University. So he wants to ask, when using the CCM approach with unfamiliar field or chemistry mechanism, how can we decide which species should be used in the low-dimensional manifold?
Very good question. First of all, the CCM dimension usually is not very sensitive. I would say not sensitive to field. It's more sensitive to the problem. So if you have a PPC engine or SCCI engine, the low dimension CCM dimension will be different. So having said that, I would suggest to use a 2D simulation or simple configuration simulation and to test different CCM. And we have a standard recommendation of CCM dimensions, system variables, and for many fields we use, they are actually quite okay, quite similar. But one recent story was that we work with industry MAN who use our CCM model, and there is some issue with the CCM dimension, and we quickly found that and suggested a little bit modification of the CCM variable, and then it works well. One can use also one-dimensional configuration, I think, to test the CCM mapping. Yeah, I hope I answered your question.
Yeah, we have 2 more questions oncoming. So there's Tian Han from Southern University of Science and Technology in China. So he had a question about CCM's generalization. So they have done some double flame modeling work showing that a leading cool flame can enrich the radical pool for the trailing hot flame. This double flame structure may change the traditional hot flame manifold. So the question is, do you think the CCM can apply to such flames with no or slight modification? If so, how to implement the method?
Okay. Yeah, very good question. We have tested many flames. We almost use always CCM to study different flames or engine conditions, including, I guess, the leading cool flame case. And I think the standard CCM variable can do a good work. But like I said, one can use perhaps a low dimensional physical space, 2D or 1D simulation to verify. I know that it can be harder to to generate a 1D representation of the problem that you are talking about. Yeah. But yeah, one can try the standard CCM, and then I think likely that it will work quite okay. That's our experience. We have a long list of publications here to setting our points, assessing our work, and you see that many results, including reformer gas simulation, and also the DTU group has been using it. So it seems to work well. But of course, if it doesn't work, then we need to work on it. Like a CCM is not an automatic approach. We use, we need to understand the problem a bit. And then since you have a cool flame or somewhere, you need to have a dimension to represent the cool flame.
Yeah. Thank
you. I hope I answered.
We also have a question from Professor John, I think.
Yes, okay. Thank you very much, Professor Bai, for the very nice talk. So I have one question about DKM. Okay, I think it was given on slide 49. So there actually we have a group of particles, right? So do we need to first, calculate the properties of this group of particles and then consider the effect? I mean, when you distribute the effects on the gas phase, right? So here, do we need to consider the weightage for different, cells, different urea cells here?
Yeah, this is a new method. We haven't tested for many different conditions, but we do use it to study 3 different types of gasifiers. We currently fix the distance of Dmax, which is the domain of distribution.
Okay.
Based on it's a user defined parameter. We set a Dmax roughly equal to 3 times of the equivalent diameter of a parcel. The equivalent diameter of a parcel means that all particles, if you lump them to one particle, then you have a bigger diameter, so 3 times.
Okay, because I guess it will homogenize, the effect of the droplets on the gas phase, right? For example, actually, some droplets actually only, lies in one cell, right? But the effect of the droplets on the gas phase will be homogenized, right?
Yeah.
Yeah, because droplet actually flame interaction, let's say we have flame, okay, also in the domain, is localized. So if we use this method, actually, is it possible, for example, to capture the interaction of the droplet or individual droplet and a propagating flame? Is it applicable for this kind of problem?
If I understand you, so you're thinking that if you use DEM, then you don't need this method. If you use MPPIC, some of this collision and the droplets itself, of course, can physically collide and being homogenized. That is taken care of by MPPIC partially. However, if the parcel, like I said, if you have 1 million particles in one parcel, then the collision will not do the work. You have to distribute it.
Oh, okay.
We distribute the source term as well, source term.
Okay. Another small question is, in your method, do we still need to make sure the particle diameter should be less than the urine cell or not? Okay.
No, we don't do that. Because if you do that, then there will be no problem. The problem is when you have a complicated boiler or furnace with a very small angles, corners somewhere, you are unavoidably having small cells. And if your particle is in that cell, it will cause problem.
Okay.
And it's very difficult to assure that you can do that unless you use a uniform grids.
Okay. Okay. Thanks. Yeah. I think we also have questions from the Q&A, Leo. Yeah.
Oh, we just came a couple questions relevant to the particle models. So Professor Bai, this is Xue-Song from Polytechnical Debari. So for curiosity, how about the correlation between the mesh size and the parcel numbers? So basically, parcel method is kind of coarse process, but no Lagrangian phase. So for your results, the parcel number will be very sensitive to the mesh size. Is that correct?
Yeah.
Okay.
I have a figure. This one I'll try to tell. What we tested. So with the fine mesh, we need to have more parcels, simply because then we have a lower load, particle load, lower. If you use fewer parcels, then the load, the local load will be high, and then eventually it will diverge. This triangle means PCM did not have solution at this point. With the distribution, then we distribute away the source terms as well as the solid volume fraction, and it became rather independent. We want to refine grids, but we don't want to really follow this line using very fine grids, very many parcels. If I did not answer your question, can you repeat again? Did I answer your question?
Xue-Song, if you're free, feel free to add, or otherwise, I think that's good. I actually have a question for you, Professor Bai. So my understanding for CCM is it's sort of a chemistry, I could be wrong, it's a chemistry accelerator from Wolstead approach. So if you're going for, let's say, stratified or swirl, you are needing, let's say, 4 or 5 conditions, as if I remember correctly. Yeah. So does that mean that for a simple, let's say, LES case, because you wouldn't have TCI, does that mean that you have to have extremely fine grid or it close to DNS to have enough cell for each grouping?
I mean, the CCM mapping is like this. We have phase space into physical space into phase space. We use, of course, for simplicity, we use rectangular grids in phase space. But then we also make a note that if there's no physical particles, then this phase space is not active.
Okay.
So even though we have many dimensions, the actual points in phase space is significantly less than the points in physical space. For example, here we can see this is determined by the physical problem. Here in the center, we have many, points, physical space points, but they belong to the same phase space. For example, A here is corresponding to point here. B, which is here and then is corresponding to this. Because B has many points like B. So we don't worry about the larger dimension of CCM because it doesn't fill up entirely the phase space, and we just need to index it in the coding that we have wasted phase space more or less. And this also shows, I think here, in case if you use low dimension, the problem is that you have many abnormal physical space points, which has to be treated as standalone physical points. So this will actually make this ratio here, here is one phase space corresponding to 20 physical space. And with that low dimension, this mapping will not be so high, I would say.
Thank you. Thank you for answering the question. I think that's everyone. Thank you very much for giving us the talk. Yeah.
It's really my pleasure to share our work with so many audience. And please feel free to contact us if you have any questions. Thank you.
Yeah, okay. Yeah, thank you very much, Professor Bai, for the very nice talk.